Greetings everyone, welcome back to Calculus. Time to start talking about more applications of derivatives, but before we get to the real big one in curve sketching, we need one of the major calculus results. The mean value theorem is what this lecture is going to talk about. Before we get to the main one though, we need to start with what's called Rolle's theorem. Rolle's theorem basically gives us the idea that if you have a continuous and differentiable function and you have a closed interval that it is continuous and differentiable on, and the endpoints have the same output value, then there must be a derivative equal to zero critical point somewhere in between A and B. Okay, so that's basically what this is saying, right? It has to be continuous and differentiable on some interval A to B, and the endpoints have to have the same output value. If all of that is true, then Rolle's theorem says there must exist at least one critical number in that interval A to B, and not the undefined kind, okay? Because it said differentiable everywhere, right? So it's not going to have a derivative equal to zero, so it won't have a cusp somewhere in between. It won't have a break anywhere in between because it's continuous differentiable. Okay, but if the two endpoints are equal, then there has to be at least one critical number where the derivative is equal to zero in between A and B. That's what Rolle's theorem says. Okay, and it's a real simple proof here. I have one of the three different cases drawn out, and it's the same argument for any of them. But imagine I have a function between x equals a and x equals b, and notice that the y value is the same for both. So f of a equals f of b. If, for say in this particular thing, I do the direction where the function goes above the points and then comes back down when it hits the other endpoint. Well, remember from our previous section, the extreme value theorem of functions say if you're continuous and differentiable on a closed interval, then that function must attain a maximum, an absolute maximum, and an absolute minimum. All right, well, it also says that those must occur at either critical points or endpoints. And we've already said that the endpoints are equal, so they can't be both the max and the min. They have to be the same, right? Well, that means that the endpoints are either going to be the minimum or the maximum, okay? But that still leaves open whatever one they aren't. In this case, the two endpoints are the minimum when you go above, right? If I had chosen the curve to go below, the two endpoints would be the maximum. But either way, there's still a missing max or min. And since both of the endpoints are already taken, in this case as the min, then there has to be a point somewhere in between them that obtains the absolute maximum. And the only other choice is that it must be a critical point. In this case, since it's continuous and differentiable, it can't be undefined. It has to be an equals zero type of critical point. Okay? The same thing goes for the underneath, or also if you just connect the two endpoints with a horizontal line. That just means that every point would be a critical point if you do a horizontal line. So all three cases can be argued the same way, but the basic idea comes back from the fact that a closed interval function must obtain an absolute max and an absolute min. The result of Rolle's theorem basically says if you have two points on a function that are the same, right? 2 points that have the same y value, the secant line that connects them is horizontal, and therefore there must be a horizontal tangent line somewhere in between them. So anytime you can find two y values that are the same, like this, then you can slide that horizontal line somewhere, and then eventually it will become tangent to the function. That's basically what Rolle's theorem is getting at here. All right, so let's get an example. Okay, so here's how you approach one of these theorems, and you're going to use it on a function. First, you have to show that all of the conditions that it had, the criteria, are satisfied. And then once they are, you can follow through with what the guarantee wants to give you. Okay, so if I can show that Rolle's theorem is satisfied, then the guarantee is that I'll be able to find at least one value of c in this interval where there will be a critical point. Okay, so let's go through the criteria. The function cosine of 3 pi x minus 5 pi, and it's on the interval where x is 0 to 2. All right, so then the criteria are it must be continuous on the interval. Well, remember, cosine is continuous everywhere, right? It has the sinusoidal shape to it. And I didn't do anything funky in this inside of the inside here. There's no divisions by 0, no square roots, no craziness in there. So this is continuous everywhere. Differentiable also on the interval. Cosine is differentiable everywhere. The derivative of cosine theta is negative sine theta, and that works for all values of theta. And again, there's nothing crazy on the inside here. So this function is differentiable everywhere. Okay, if you have to write this out as like a proof or something, you could say cosine is continuous and differentiable everywhere. So it's definitely continuous and differentiable on this small subinterval, right? Next, f of a must equal f of b. Okay, so let's check that out. F of 0 is, you know what, let me make some space here. Right here, we have f of 0, right, because that's a. F of 0 is going to be cosine of negative 5 pi, right? And cosine of a negative, well, not just negative, cosine of an odd pi. Because remember, the negative doesn't actually matter to cosine. Cosine of negative 5 pi is going to be the same as cosine of 5 pi. But cosine of an odd pi gives you negative 1. All right, so then if I plug in 2, f of 2 is going to be cosine of, I've got 3 pi times 2, which is 6 pi, minus 5 pi, which is cosine of pi. And again, notice that gives me negative 1. All right, so that also is one of the criteria, right? F of a must equal f of b. So the function is continuous and differentiable, and the y values of the endpoints are equal. So the criteria of Rolle's theorem is satisfied, right? All of the conditions that are needed for Rolle's theorem are completely true. So Rolle's theorem is guaranteeing that on 0 to 2, I will find at least one critical point, critical value of x, where the derivative is equal to 0. So let's find out. Let's find at least one of those. Take the derivative. 3 pi, oops, forgot. 3 pi is the inside derivative, right? That's chain rule. And then derivative of the cosine is going to give me negative sine of the inside. Right? There's my derivative. And it's saying that I should be able to find a point where this is equal to 0. So I just need to solve this equation. Okay? Divide both sides by negative 3 pi, and 0 divided by anything is 0. So really and truly, this piece is just going to divide away. And what I'm left with is 0 equals the sine of something, right? Well, remember, sine equals 0 anytime the inside, anytime the thing plugged into sine is some multiple of pi. Sine of 0 is 0, sine of pi is 0, sine of 2 pi is 0, sine of 3 pi is 0, so on and so on. So that means that 0 equaling this sine right here is telling me that the inside, the 3 pi x minus 5 pi, must be equal to n times pi, where n is restricted to being an integer only. Remember, that's what the capital double line Z means. N can be an integer only. In other words, 0, 1, 2, 3, negative 1, negative 2, negative 3, just the positive, negative, and 0 whole numbers, right? That's only going to be true when n is one of those integers. So then from here, I can get x by itself. First, I'm going to start by dividing everything by pi. And then I'm going to add the 5 and divide by 3. So I have x is 5 plus n divided by 3. So x could be several different things here, okay? Because n can be any whole number, positive or negative or 0. That's what this is saying. So there's an infinite number of these things here. I could pick 100, right? 5 plus 100 would be 105 divided by 3. The problem with that is it wouldn't be in the interval 0 to 2. But if I pick a few good values of n, right? For example, if I pick where n is 0, 5 plus 0 over 3, x would be 5 over 3, which is definitely less than 2. Okay? What if I pick where n is 1? Right? Well, if I pick where n is 1, 5 plus 1 is 6 divided by 3 is 2. And that's one of the endpoints. That's not what we're interested in. However, if I go backwards, like n equals negative 1, then I can get that x is 4/3. Or if I pick where n is negative 2, I can get where x is 3/3, which is 1. I can pick where n is equal to negative 3, which would give me x is 2/3. And what about when n is negative 4? I could also pick where I'm getting x is 1/3. If I pick negative 5, I'm going to get 0/3, right? Which is going to give me 0, which is one of the endpoints. And you could probably count the 2 endpoints, but I'm not going to because we said it needed to be in the interval. But as you can see, I found at least one point, at least one, right? In fact, I found 5 x values in the interval 0 to 2 where the derivative was equal to 0. All right? And Rolle's theorem guaranteed that because the 2 endpoints were equal and it was continuous and differentiable on that interval. That's what Rolle's theorem does for us. Okay? If you can show that 2 endpoints are equal and it's completely continuous and differentiable, there's going to be a horizontal tangent somewhere in that interval.
Let's get a visual on that particular function for Rolle's theorem here. Here's the cosine of 3 pi x minus 5 pi. It's really just a cosine curve that's been compressed differently and been shifted. That's all. So we have this cosine function, but we're only interested in the interval from 0 to 2. So I turn on just that piece, and notice it's just this part of the graph here. Okay, so looking at this piece of the graph here, we notice first that at 0 it's negative 1, and at 2 it's also negative 1. That was part of the criteria for Rolle's theorem. And then from there, Rolle's theorem guaranteed that there would be at least one point in between these 2 endpoints that would be a tangent line critical point. Notice we have 5 of those at these different locations. And they're exactly the ones that we computed at 1/3, at 2/3, at 1, at 4/3, and at 5/3. You can see that those are all of the points where the derivative is actually equal to 0.
Okay, everyone, now for the main event, the mean value theorem. It's basically a generalized version of what you just saw with Rolle's theorem. Rolle's theorem is only for when the function values are the same and the secant line is horizontal, so we're looking for horizontal tangent lines. The generic version of mean value theorem takes any secant line between any 2 endpoints as long as the function is continuous and differentiable. You can take any secant line between any 2 points there, and you'll find that there will be a tangent line parallel to that secant somewhere on the function. Let's read through it here. So if f is continuous and differentiable, which technically I guess we could say as long as it's differentiable, because that implies continuity. The differentiable part is important because we don't want breaks and we don't want cusps. It needs to actually be differentiable everywhere on the open interval a to b. Okay? If that's true for your function, then the mean value theorem says that there will be some c value in the a to b interval such that the derivative at c is going to be equal to the slope between a and b. Notice that's what this is, right? Y minus y over x minus x. This is the slope of the function, the average slope, the secant line slope between a and b. And then, of course, this is the derivative, which is the tangent line slope. Another way to interpret this is that the instantaneous slope somewhere in between a and b, right, that's x equals c, is equal to the average slope. Or the instantaneous rate of change is equal to the average rate of change of some whole trip. Okay? All the mean value theorem guarantees is if it's differentiable, continuous, the whole stretch, the whole interval, there will be at least one point where the instantaneous slope is equal to the average slope, right? So like this, as long as it's differentiable, continuous on some interval from a to b, then if you find the secant slope, right, the secant line, there will always be a point somewhere in between a and b where the tangent line is parallel. So the instantaneous slope is the same as the average slope. The proof of this is just an extension of Rolle's, really. Rolle's theorem came from the extreme value theorem. So then we keep building here by saying, let some function b of x be the difference between the secant line, right? So that's this line right here, and the function. Okay, so in other words, b of x is going to be whatever you calculate the difference between these two to be. From here to here, at every point, would be b of x. Right? So the difference here, the difference here, at every x value between a and b, okay, b of x is just the function minus the secant line. Okay? Well, the secant line is just the average slope, I'll use m for now for average slope, times x minus a plus f of a. Right? Because it's just a line that goes through the point a comma f of a, and therefore the secant line is just m x minus x plus the y. That's just using your point slope formula to create the equation of a line. Okay? Now remember, this is the secant line, so this m that I've written here is the slope between these 2 points. If you take the derivative of b, before we do that, b of x defined the way it is right here obeys Rolle's theorem because it's continuous, because f is continuous and the line is continuous, and they're both differentiable. And the two endpoints of b are 0 because the function and the secant line meet up at those 2 points. So f minus the secant line at the endpoints is 0 and 0. So notice b of x obeys Rolle's theorem on the interval a to b. Which also means that if I take the derivative, I'll be able to find a b prime of x equal to 0 point somewhere in between a and b. I have to be able to find that because it obeys Rolle's theorem. So if I take b of x, that's going to be f prime, and the derivative here is just the slope, right? Because everything else here is a number. The a is a number, the f of a is a number. M times x, the derivative is just m. But then there's supposed to be a critical value somewhere in there, right? At some value c. So actually this shouldn't be x. The critical value b prime of c. So that'll be f prime of c everywhere here. Right? So if it's equal to 0, then basically I just add the m over, and it shows that the m has to be equal to the derivative, or rather the derivative at c is equal to m. But remember, we said up here m was the slope of the secant line. So that means my derivative at c is equal to that slope of the secant line. Okay? As long as f was differentiable, then b was differentiable, so was the secant line, right? So basically it just follows from a really crafty twisting of Rolle's theorem there. So you can take any function that's continuous on a closed interval, okay? And then you create the secant slope from endpoint to endpoint, and then there will always be some point between those two endpoints where the tangent slope is exactly equal, okay? It's a continuity thing. If I'm going to go from this point to this point, at some point I've got to turn in order to make that happen, right? So in making that turn on the graph, it's got to equal the same slope at some point to be able to go above it. Here's another way of thinking of this. This is also the mean value theorem. They call it mean, kind of like average, right, is mean. They call it the mean value theorem because the average rate of change is like the mean change across the whole thing. It's an average change. And it being equal to the instantaneous is like giving it some sort of reality. Here's an example. I've heard rumors of this being true. I've never actually experienced it, but I've been told that there were places where some cities had set up with their police departments a point A and a point B on some turnpike that you would have to drive, and they would measure. They would give you a little stub when you enter point A, and then they would take the stub at point B. So in other words, they knew the time when you started and the time when you stopped, right? So they know the distance also. If your speed on average, in other words, you do B minus A of your time, and then distance divided by time is an average speed that you took to go the whole distance, right? So they know your average speed because they know your beginning and ending times. If that average speed was more than the speed limit of the turnpike, then because of the mean value theorem, they know for a 100% fact, because your trip is differentiable, because you can't just disappear and reappear in another spot. It can't be discontinuous, and you don't, your speed doesn't spike and then all of a sudden change into something else instantaneously. You can't stop instantaneously. You have to slow down, speed up, and things like that. So every bit of your trip is differentiable as far as time is concerned. Okay, so they know your average speed, and they know that according to the mean value theorem, since your trip is a differentiable function and your average speed is more than the speed limit, then at least one point somewhere in the trip, your instantaneous, in other words, at that moment speed, had to be equal to it. So they know that at least one moment in there you broke the speed limit, mathematically proven, and therefore they could write you a ticket. Again, I don't know how true that was. I've only been told that, but it's an intriguing idea that it is mathematically proven because our existence is continuous and differentiable according to time, that if your average speed was more than something, then at least one point of your trip, the instantaneous slope, the instantaneous rate of change, your instantaneous speed, had to be equal to that average, which is more. So at that one moment, you were breaking the speed limit, right? Interesting. Okay, so let's go through a few examples with mean value theorem here. So start with a couple of examples right here where it fails. Let's talk about it for a second. I have f of x equals the absolute value of x on the interval from -2 to 3. So on the interval from -2 to 3, that would be on my absolute value graph something like from here to here, right? This would be my secant line. Now notice it fails visually. There's no point where the secant slope right here is the same as the tangent slope. And that's, you can tell because the absolute value functions are linear, right? Each side is linear, so it's either this slope or that slope. So then you're like, wait a minute, it fails. Mean value theorem's a sham. No, 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 no. We broke a rule. Mean value theorem makes no guarantees on intervals that are not differentiable, right? From -2 to 3, there's one point where the absolute value of x is not differentiable, and it's at that cusp. At x equals 0, the derivative of this function does not exist. So it fails the criteria for mean value theorem in that sense. Okay, there's one non-differentiable point, so the whole thing's off. Notice if I were to pick 2 points from the same side, the slope would then, of course, equal the derivative because they're both lines. All right, but because I included the cusp in the interval, the mean value theorem does not apply. In a of x here, I have ln of 5x minus 7. Of course, that looks like a normal function that should obey mean value theorem, right? I can get secant lines and things like that. But then look at the interval, 7/5 to 2. 7/5 happens to be the point right here where I would get the ln of 0. That actually corresponds to the vertical asymptote. So I'm not continuous on the closed interval, okay? And also, it's not really differentiable totally on the open interval either, because the derivative at 7/5 should technically be a negative infinity type of thing, right? It should be, positive infinity, I guess, if you're coming from this way. The derivative will be positive, the function value is negative infinity, but then infinity is not really a value, right? So the problem here is the 7/5 is a vertical asymptote, okay? It's not even going to be totally continuous on that. It would only be continuous, well, it wouldn't even be continuous from the right either, because it doesn't actually have a function value there at 7/5. It's a vertical asymptote. So mean value theorem, again, doesn't apply because the interval is not, it's not continuous on that interval. 7/5 is not even in the domain of this one, right? So for both of these, you would say fail, right? As far as mean value theorem is concerned, they don't obey the mean value theorem. Okay, here's an example of one that does obey it. 4x to the third minus 5x plus 3. It's polynomial, so we know it's continuous everywhere, differentiable everywhere. Okay? So what I want to know is what points on this interval have a corresponding slope, right? So I can find a secant slope, I can find an average rate of change from -1 to 1, and then I can also show where the values between -1 and 1 are, where the tangent slope is the same as the secant slope. So let's see. First, let's start off by finding the secant slope, right? M is going to be g of 1 minus g of -1 over 1 minus -1, like that. Okie dokie. So then from here, g of 1, if I plug in 1, I'll have 4 minus 5 plus 3, which is going to be 2. And then minus g of -1 is going to be -4 plus 5 plus 3, which is 4. And then on the bottom, I've got 1 plus 1, which is 2. So I've got -2 over 2. I've got a slope of -1, average slope. Okay? So if you look at the graph of this, the two different points on the graph, it would be more like this, the two different points on the graph, there's a secant slope, an average slope of the line that connects those 2 points is -1. So now let's find the points on that interval where the tangent slope is equal to that same secant slope. So first, let's start with the derivative, right? G prime of x is going to be 12x squared minus 5, right? Then I'm going to set that equal to -1. All right, and then I just need to solve this equation. I'm going to add the 5 and divide the 12. So adding 5 gives me 4, divided by 12 is equal to x squared. 4 over 12 reduces to 1/3, and then I can take a square root. So at both plus and minus square root of 1/3, I have an x value. Well, let's double check and make sure, right? The square root of 1/3 is 0.5773, 0.5774. Okay? So both of those are in that interval from -1 to 1. Both of these points are in that interval. So there are actually two C values, right? C values from mean value theorem would be C equals square root of 1/3 and C equals negative square root of 1/3. And again, remember, these are x values, and what these x values give us are locations on the graph where the tangent line is parallel to this particular secant line between -1 and 1, okay? So I don't have a good way of drawing this 100% to be able to show you, so I want to show you in GeoGebra what this looks like, okay? Go take a look.
Here's the function that we were just talking about, 4x cubed minus 5x plus 3. Notice I did have to extend the x scale a little bit here because the original one was a little bit hard to see. It was a little too thin. We can even zoom in a little bit more here. So then take a look. The 2 points, the endpoints, were here and here when x is -1 till x was 1. So we're really only talking about a small section of the function, just this piece of the function right here. Notice the secant line between those two endpoints looks like this, and the points that we found the derivative to be parallel were at negative square root of 1/3 and positive square root of 1/3. Those are these 2 points here. Look at the tangents at those points. Notice the slopes are -1, you can see from the equation over here. And you can tell that all 3 of these lines are indeed parallel. So this is what the mean value theorem has done for us. We were able to take a slope from 2 endpoints and show that there were at least 1, in this case 2, points on the function where the tangent, the instantaneous slope, is equal to the average slope.
To finish up this lecture, I just wanted to make a couple of comments about some extra results. If you're looking for the pure proof on these, I suggest you go and read the OpenStax chapter on mean value theorem from their Calculus 1 text. It's completely free, and I found them to be rather efficient and succinct ways of talking about these particular topics. But they are important results, and they do lead into our next topic, so let's talk about them for just a second. Because of mean value theorem, we can actually prove that for the functions f and g that are continuous and differentiable on the interval, if the derivative is 0 at every point on an interval, if you can show that just the derivative equals 0, right, f prime of x is 0 and it's like a whole interval, then that means for that whole interval, the function must have been equal to a constant. F of x equals 10, f of x equals 9, f of x equals -2000, whatever. Okay? If you show that the derivative is 0, and we've talked about this, right? We said that the derivative of a constant is 0, but we're also starting to build a little bit of the groundwork here for later on when we want to start reversing derivatives. Okay? Eventually, we're going to want to talk about how we have a derivative that is 0. What could that lead to? Oh, well, then that means the derivative is, the original function, is constant. Okay, there are no other options. So we said that the derivative of a constant is 0. But now what we've shown is that the only thing whose derivative is 0 is a constant, right? It's the reverse, the only if to the if you will, right? From that result, you can build, and most of these, by the way, are proofs by contradiction, but you can build off of this result
that if you have two derivative functions that are equal on an entire interval, like every single value they're equal, then that means the only way that that can happen is that their two functions can only differ by a constant that never changes. So if f prime and g prime are equal on some interval, then the function f of x and the function g of x are only going to be different by plus some number at the end, right? So if f of x is x squared plus 10x, then g of x might be x squared plus 10x plus 7, or x squared plus 10x minus 1. But that also means they could be completely equal because that constant could be 0, okay? So that is a possibility. But at most, they only differ by a constant. This is going to be very important when we start doing antiderivatives in the next chapter. Now, for the very next lecture, when we start talking about how we want to get into curve sketching and what the derivatives can do for us, this is a major result leading into what we call the first derivative test of a function. And basically, it allows us to say that if you can find a complete interval where the derivative is all one sign, in other words, the derivative is all positive or the derivative is all negative on some interval. So you have a complete interval and you know for a fact it's all the derivatives are positive in this interval, all the derivatives are negative in this interval, whatever. Then you know that that's an interval where if the derivative is positive for the whole interval, then the original function is increasing over that entire interval. Okay? And then same thing, if the derivative is negative on a whole interval, then that function is decreasing on that whole interval. And I know we've probably mentioned this before, and you've probably done some ideas where you could draw the graph of a derivative from the original, where if it's decreasing, then the derivative should be negative everywhere. But now, again, this is a result where we can take information from a derivative and use it to help us go back to the original. So even though if I have, say, the equation of a function, I can take the derivative and then find all of these different intervals, and then I'll know something about what the graph of the original function should look like. Okay, so these two results also come from the mean value theorem. And I really recommend you go and read the proofs of these. They're very interesting. They're very short usages of the mean value theorem. Okay? I hope this has helped you understand the mean value theorem and how it is connected to a lot of our important results that we're going to be using. Stay tuned for curve sketching over the next couple.